With video 8, we're looking more at the properties of these molecules. So we're looking at molecular polarity, and polarity is already a word we discussed. If a bond is polar if the electrons aren't being shared equally. So in the hydrogen and chlorine, which is the exact molecule we looked at previously with this, and we had the different colors on the hydrogen and the chlorine atoms to show electron density. Chlorine has a higher electronegativity, so the electrons are pulled that way, and a bond dipole can be shown as an arrow pointing in the direction of where the electrons are moving. We cross the other end to show our positive sign, or we show it as these dipoles with the lowercase delta, partially negative, partially positive. But if we have a molecule, we have to look beyond just electronegativities because we have to understand in whole which way are the electrons being pulled. So a bond dipole is the overall dipole moment due to the atoms in that bond. It always points towards the most electronegative atom or atoms. It depends on how big of a difference there is in electronegativity because that determines how unequally the electrons are being shared, but we also have to pay attention to the direction of these because these are vector quantities, and that will mean something to you or it'll mean a lot to you if you've taken physics, some math classes, I'm sure. But the idea is it's not just how strongly the electrons are being pulled, but in what direction they're being pulled. So the classic example that we use to compare these things is CO2 and H2O. CO2 is a polar bond. The electronegativity on oxygen is 3.5, carbon is 2.5. The difference between those is 1.0. So that is considered polar, and the electrons, as drawn here, are pulled towards the oxygen to the left. They're also pulled towards the oxygen on the right, but because they're being pulled equally in opposite directions, we don't have an end of our molecule that's negative and an end of the molecule that's positive. We have no overall dipole. The pull to the left cancels out the pull to the right. But in water, with oxygen again at 3.5 and hydrogen at 2.1, we have an electronegativity difference. Electrons are pulled towards oxygen, electrons are pulled towards oxygen, but because this is a bent shape, and we can know that because there's lone pairs right there. So we have two bonding regions and two lone pairs. It is a variation on tetrahedral electron geometry, or specifically the molecular geometry is bent. So there's some pull inward and some pull inward. Those cancel out, but they're both pulling upwards towards oxygen. So the molecule as a whole is polar. So we can have unequal pull for electrons, but if they're in opposite directions, we can have still an overall equal distribution of electrons because there isn't a negative and a positive end. So when we're looking at molecular geometry, there's one key word that you'll see in a lot of these definitions, and it's down there at the bottom in bold, underline, and all capitals. But the first thing you have to do is you look at your electronegativity and determine if your bonds are polar. Your bonds have to be polar for your molecule to be polar. And you may be given electronegativity values, or you may just be asked based upon the formula. So you kind of need to have a feel for what's polar and what's not. But in general, the farther the atoms are from one another on the periodic table, the more polar they are. If there's more than one element between them, either side to side or top and bottom or diagonally, then they're definitely going to be polar because that electronegativity difference is big enough. So then you look at the central atom. If it is symmetrically surrounded by identical atoms, it's nonpolar. The carbon is symmetrically surrounded by oxygens. But the lone pairs will change the shape sometimes. There's no lone pairs here, there are some here, which makes the molecule polar. If it's surrounded by different atoms, it can be nonpolar or polar depending on the symmetry. Here it's the same atoms, but the lone pair changes the shape, and the water molecule is asymmetrical in the way it's drawn. It's asymmetrical up and down, or in the y-axis, I guess. It's symmetrical across here, but it's asymmetrical up and down. When you're explaining molecular polarity, the easiest way to do it is to use the word symmetrical or asymmetrical. It's polar if there's an asymmetrical pull for electrons. It's nonpolar when the molecule is symmetrical and all of the electrons are being pulled equally in opposite directions. So there's lots of other descriptions you may see out there, but kind of the fastest way to get to the point is to say this molecule is symmetrical. Electrons are pulled equally in all directions. It's nonpolar. Or because the molecule is asymmetrical or not symmetrical, electrons are being pulled more in one direction than another direction. That will get you to the point much faster than trying to describe things about the shape and the difference between the molecular and electron geometry and bond angles and a lot of those other things. So we'll jump into some examples here. So for each of these, we're going to start by drawing the Lewis structure. I'm also going to mention the bond angles and the shape just as good practice. It's not required there, but then we'll talk about if there's a dipole and if it's polar. So the first one here is SO2. With each of these, you're following the same rules: 6 electrons on each sulfur, 6 electrons on each oxygen, 18 electrons. Sulfur in the middle, oxygen's outside, fill the outside with dots. Once we've done that, we've placed 8 electrons on the left, 8 electrons on the right, so that's 16. 17, 18 can go right there. And when we do that, we still don't have an octet on sulfur. So there's a couple different resonance structures we can show here, but we're not going to get into all the resonance, but we definitely have to have at least a double bond on one side. Actually, I'll show really quick the other resonance that's totally equivalent to this, which would be that one. And this is a situation where you can actually draw a third Lewis structure that is kind of in between these. Well, excuse me, not just in between these, but because sulfur can have an expanded octet, we could have a double bond on each side and still have that lone pair and use 18 electrons, but all three of these have the same shape. The bond angle may be slightly different because of the single versus the double bonds repelling one another, but they all have the same shape. We could do formal charges and see which one's most likely, but since we're not asked about that, we're going to focus on what we're asked about. So as we're looking at this, we want to think symmetrical, asymmetrical, and looking at it, it's not just how we draw it, but it's how it occupies space. So there are 3 electron regions. No matter which drawing you look at, there's electrons bonded to the one oxygen, electrons bonded to the other oxygen, and a lone pair. 3 electron regions is trigonal planar, but one of those regions is a lone pair region, so the molecule is bent. So without any electrons, we could draw this and it would look like that. The bent shape makes it asymmetrical, much like water. So then we think about where are the electrons being pulled. They're being pulled towards oxygen. They're being pulled towards oxygen for an overall dipole, which is down towards oxygen. The direction of the dipole is towards the oxygens. So we drew the Lewis structures. We thought about the geometry because that helped us to know if it was symmetrical or not. It ended up being bent. We looked at what had a higher electronegativity, which was the oxygen, so the electrons were pulled towards the oxygens. The second one here is kind of a weird polyatomic ion. We've got 5 electrons on chlorine. We've got 5 on phosphorus, 4 sets of chlorines, but we've got a positive 1 charge. So we have 28 and 5. This will be 32 electrons. Phosphorus in the center. Chlorine, 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 chlorine. Phosphorus and chlorine are not directly next to each other on the periodic table, so we would know that these bonds are polar, even if we don't know the exact electronegativities. And then it's good to show our charge here. Then we think in terms of shape. 1, 2, 3, 4 bonding regions, 4 electron regions. So this is tetrahedral, both in electron geometry and in molecular geometry. And all of the sides have the same thing on them. They're all the same atom, and then every direction is B. There's no lone pairs where we don't have an attraction for electrons. So this is perfectly symmetrical, and there's no dipole moment. So non-polar, even though the bonds are polar. PCl6 is another kind of weird polyatomic ion. Sorry, spaced out there for a second. We've got 6 chlorines, each with 7 valence electrons. Phosphorus has 5. The extra charge has 1, so we have 48. We've got chlorine, 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 chlorine. The reason we're able to have an expanded octet is that phosphorus is in period 3. Things in period 3 and lower can have expanded octets because the nucleus and the atom is large enough to accommodate the extra bonds. When we have a polyatomic ion, we put the brackets around it, and when we look at this, we've got 1, 2, 3, 4, 5, 6 electron regions. That is an octahedral electron geometry. 1, 2, 3, 4, 5, 6. All of them are bonding regions, so octahedral bonding geometry. Even though phosphorus to chlorine is a polar bond, it's being pulled equally up, down, left, right, front, and back, and is non-polar overall. When you're looking at your central atom, if I were to go back really quick when I was drawing my SO2, however I had that drawn, my central atom, as I look at it, has 1 thing attached to it, 2 things attached to it. Those are the same, but the electrons are different. So those 3 things aren't the same as each other. That is my clue. It's going to be polar. Here, all of the things that are on the phosphorus are the same, 6 chlorines. So that will be non-polar. So when you're looking to symmetry, it's important to think about shape, but you can just look at your drawing as well, as long as you've done that correctly. And the last one here is CH2O. So carbon's got 4 electrons, 2 times 1 for my hydrogens, 6 there. So 12 electrons, carbon in the middle. Attach it out to these things. Hydrogen doesn't need any more electrons, but the oxygen does. We've placed 2, 4, 6, 8, 10, 12. The oxygen and the hydrogens are good, but carbon still only has 6, so some of these get scooted in. So then if we wanted to look at this carbon-hydrogen bond is right at the edge of being polar and non-polar. But the carbon-oxygen bond, we've got an element in between there, so that's definitely a polar bond. So we do have some polarity in terms of our bonds. When we look at what carbon's attached to, it's attached to some oxygens and, some hydrogens and an oxygen. Those are not all the same thing. That's asymmetrical. This is a polar molecule. We can also think of that in terms of electron geometry. We've got 1, 2, 3 electron regions. That's trigonal planar. 1, 2, 3 of them are bonding regions, still trigonal planar. So that 120-degree angle here between all of these, we've got different poles for electrons, and the pole for electrons is greatest in this direction. There's actually a slight pole this way, a slight pole this way, and a big pole that way. So our dipole moment is going to be towards oxygen. So once again, a new skill that we start by drawing the Lewis structure. Then we look at our bonding regions, we look at our lone pairs, we look at what's connected to it, and we can know something else. When you're asked if something's polar or non-polar, it's still based upon the Lewis structure, so make sure you're drawing that. From here on out, we're just kind of explaining in more detail how this is happening. So a lot of the skills, a lot of the questions, a lot of the free response are these things up till now, but you'll definitely have some stuff about bonding theory. There's some important both multiple choice and conceptual stuff things yet to come.